Main problem of suggested Science Slam video is a critical engine term. For simple illustration of this problem, we want to present behavior during flight of twin-engine model using flying simulator with left engine critical. Critical engine in aviation describes engine a failure which would most affect the performance or handling abilities of an aircraft. On turbojet/turbofan aircraft, there usually is no difference between the yawing moments after failure of a left or right, outboard, engine. Considering propeller aircraft, there is a difference in the remaining yawing moments after failure of the left or the right engine when all propellers rotate in the same direction due to the P factor. It is important to note that this example depends upon both propellers turning clockwise as viewed from the rear. On aircraft with counterclockwise turning engines, the right engine would be critical. Extremely dangerous situation appears when failure of critical engine occurs at stage of airplane land and takeoff. It is also important to mention that failure of critical engine causes a heavy load on the remaining engines. Due to the asymmetric blade effect, the right-hand engine typically develops its resultant thrust vector at a greater lateral distance from the aircraft's CG than the left-hand engine. The failure of the left-hand engine will result in a larger yaw effect than right-hand engine. Today's engineers and designers focus on improving onboard flight systems, reducing human influence. Of course, it's impossible to exclude human from task of piloting, but it is advisable to support and take over part of his work for better safety. Modern passenger airplanes equipped with advanced electronic systems respond automatically to situations like damage of one engine, reducing threat of flight stability loss. For example, system called FADEC constantly monitors each engine during flight. In a situation of engine failure, system recognizes decrease of thrust by engine pressure ratio, and with a slight delay, change thrust ratio on remaining engines. This system fully prevents any manual intervention, giving full control of performance for onboard computer. During the design phase of the aircraft, the tail design engineer sizes the vertical stabilizer/tail to comply with the controllability and performance requirements after engine failure. Engine effect is not a dangerous for multi-engine aircraft. For example, we use geometry of own model. In our project, we have designed double-tailed aircraft for better stability and to comply of controllability in case of SEV. We have used four-engine as propulsion system, reducing developing yawing moment causing flight stability loss in case of engine damage. In our aircraft, propeller rotation is clockwise causing left engines critical. During the flight, in case of engine failure, our pilot for recovery of stability had to change thrust on remaining engines and comply controllability with vertical stabilizer and ailerons. During the stage of design we considered of course variables such as minimum control speed, which is measured while the critical engine fails or is inoperative,